Hi everyone, what's up? Today I want to talk to you about how you can miss a solution using separation of variables to solve a differential equation, okay? So today, to prove my point, I'm going to use this example here, okay? So we're going to solve this differential equation. And before we do that, I know you're probably wondering what the hell this notation is. I know it looks pretty fancy, d over dx plus x. This is just something called the annihilation operator in quantum mechanics. And in quantum mechanics, this operator basically lowers the number of particles in a system in a given state. I don't know that. I don't know pretty much anything about quantum mechanics. I just read that on Wikipedia. So yeah, I got this example, by the way, I should mention. I don't know any quantum mechanics, so the origin of this example is from an MIT course by Professor David Jerrison on MIT OpenCourseware. It's MIT's single variable calculus course. And this problem it's on, I think it's the fifth problem set, I'm not sure. But the thing is, yeah, this is just a problem that I didn't come up with, okay? So all credits and copyrights go to Professor David Jerrison, who definitely knows probably some quantum mechanics. I just know some things, but I don't know anything about this operator. Just what I read on Wikipedia. But yeah, anyways, that's not relevant here. Now let's solve this. Let's solve this problem. So to solve this problem, we're gonna do separation of variables, as I mentioned, and this is this operator behaves in a pretty interesting way. So one way in which you can simplify that operator and deal with something that you're probably more familiar with is by distributing y into this operator, and you're gonna get the following. You're gonna get that this is dy over dx plus xy. Okay, I know we literally just plug y into the the input of this derivative, which is probably not really something we have ever done before, but this is something from quantum mechanics, and quantum mechanics, it's pretty weird, so just don't worry about it. Professor David Jerrison, he used this example, so he's probably right. Okay, so here, we need to use his authority. So now this is the new differential equation that we get based on the first form that we had. And of course, this is going to be equal to 0. Now, to use separation of variables, you know that, we need to separate y and x and put them in different sides of the equation. So let's rewrite this. So we're going to get, this is dy divided by dx is equal to minus x times y, okay? Now we can move dx to the right-hand side and y to the left-hand side of the equation. So we're going to get dy divided by, now the negative sign, I'm going to leave it on the right-hand side. So we have dy divided by y is equal to minus x times dx, okay? So this is the new differential equation that we get. Now what can we do here? Well, we can just simply integrate, okay? So we're going to take the antiderivative on both sides, okay? This looks kind of, yeah. Let me fix that, yeah. So we're going to take the antiderivative on both sides, an antiderivative on both sides of this equation, okay? Now we know the antiderivative of 1 over y with respect to y is going to be natural log of absolute value of y. I'm going to use absolute value, okay? I'm not going to... There are many, exceptions to using absolute value or not, especially in differential equations. Based on the general solution, you can determine something about the absolute value. In this case, I'm not going to address that, okay? I just want to focus on the missing the solution part. So this is going to be ln y is going to be equal to, we have minus x, that's going to be minus x dx, and we know that it's simply going to be minus x squared divided by 2 plus big C, okay? Notice that on the left-hand side of the equation, I didn't write C. Basically, I did that because on both sides, you're going to get a constant. So you can just simply, put those constants together and just simply write C, okay? This C can be any constant, and it can represent the, the addition or subtraction, whatever you get, of the other constant on the left-hand side, okay? So yeah, this constant just represents the constant that was here plus the one that you get from this antiderivative. So now this is the result that we get for both antiderivatives. Now I'm going to use base e on both sides. So this is going to be e and this is going to be e. I'm just using base e such that I can cancel out e and ln and just get y, okay? Remember, that's a property of logarithms. So from here, I'm going to use red, so you know that, we did something tricky here. Well, not tricky, it was just a trick, simple trick. So yeah, we get that y. Now you could keep writing the absolute value. I think I'm not gonna write the absolute value, and rather I'm just gonna write plus or minus Now we have e, so this is gonna be e, and it's gonna be parentheses. Now actually, I'm gonna do it like this. We know that when we're adding two exponents, this is basically multiplying the base with those two exponents. So this is basically e to the c times e to the negative x squared divided by 2, okay? So this is going to be equal to e to the c times e to the minus x squared divided by 2, okay? So this is what we get. Now, usually, I'm assuming that if you're watching this video, you're probably you're just starting to deal with, to work with differential equations. So I think it's worth mentioning that in differential equations, usually when we get e to the c, mathematicians, they like to keep things concise, and they usually just write e to the c or e to the anything, or pretty much any other constant or coefficient that you get here for any solution of e or any solution that involves e, they just write a, okay? So we would get y is equal to plus or minus a times e to the minus x squared divided by 2, okay? And of course, how should I write this? Yeah, I'm going to say that a is equal to ec, which is equal to e to the c, which is equal to any coefficient, pretty much, okay? Because when you choose any c value, remember c can be any constant, okay? And you can get any number that you want using base e, okay? E to the something can be pretty much any number that you want, except, well, there are some exceptions, of course, but you can get a lot of numbers with that, okay? So you can just say pretty much any number, okay, with some exceptions, but yeah, I'm just gonna write any number, okay? Because then, of course, the negative, if you want to get a negative coefficient for this e, well, you could use the negative portion of the general solution, and then you just give a positive quantity, okay? So yeah, that's something you could do. So now this would be the family of solutions. This would be the general solution to this differential equation, okay? Now this solution, it's pretty interesting because it is missing, well, no, how should I, from this solution, you cannot interpret that another solution to this original differential equation is y equals 0, okay? So now if you look at this equation, you can see that if you plug 0 for y, you're going to get 0, okay? It doesn't matter how complex this annihilation operator is and how fancy quantum mechanics are. If this equals 0, well, it's just going to be 0, okay? So this differential equation would be satisfied by y equals 0. However, there's a problem with this family of solutions. If you try to find for what value do you get 0 for, I'm just going to write a e to the minus x squared divided by 2, well, it's going to be really hard to solve this. In fact, it's going to be impossible, because if you look at the graph of this function, and maybe if you're a nerd and you have seen the wave function in quantum mechanics, you don't need to know anything technical. But if you know the graph of the wave function and how the wave function, it's pretty much something like this. So let me try to make the best drawing that I can. A lot of wave functions, they look something like this. So, ooh, there's something like this, okay? And this is, if I'm not mistaken, this is like, I think it's psi squared. I think this is the function. I have not studied quantum mechanics, but I really like math and science. So yeah, I know this, and this is exactly the graph that you would get from this family of solutions, okay? So if you've ever seen the wave function and some of the graphs of the wave function in quantum mechanics, some of them look kind of like this, okay? So this function, that's exactly how it looks, okay? It is centered at 0, and depending on the sign that e to the minus x squared divided by 2 has, depending on that sign, this graph is gonna, it's gonna be on the lower quadrants of the xy plane, or it's gonna be in the upper quadrants, okay? So in this case, it doesn't matter what you do. There's gonna be a horizontal asymptote. It doesn't matter what sign you write for the function. There's gonna be a horizontal asymptote at y equals 0, okay? So there's not gonna be any number that allows you to get 0 for this function, okay? Nothing. There's nothing that you can do. Of course, if you take the limit as x approaches infinity or negative infinity works because we have x squared, so negative infinity would be equal to infinity, so it's the same as infinity. So if you take the limit as x approaches infinity and negative infinity, you would get 0, okay? But only if you take the limit, okay? So as x grows larger, since this would just simply be the same as a divided by e to the x squared divided by 2. So this would be the function that you get. And of course, if x grows larger, this fraction will approach 0, okay? So you can only get close to 0, but there is no value of x that gives you 0, okay? That's my point. That's what I'm trying to say. And that means that y equals 0, it's a solution that we're missing, okay? Because, just by inspecting the differential equation, y equals 0 is a solution, okay? But this family of solutions, the general solution, is not going to help us find that, okay? So, yeah, that's my point. That's what I wanted to talk about in this video. And, maybe, just have fun talking about things that we don't know, like quantum mechanics. I probably want to major in something with physics, and I guess eventually I will learn about quantum mechanics, but for now I don't know anything too technical about that subject. So yeah, anyways, I hope that you enjoyed this video, you learned something, and see you in the following one. Bye.